Awesome. Okay. Thank you. Very happy to be here. Appreciate the chance to share a little bit about AI from a vendor perspective. I'll introduce myself first and then introduce Deep Health and then jump into some slides. So I've been with Deep Health for about 5 years. My background is computer science. I did a PhD at MIT, but have been always been interested in healthcare applications. So in graduate school, did a certificate at Harvard Medical School, taken some of the classes I think you've gone through, like pathology and physiology and et cetera, but I only have a flavor of that. What I spend my time on now is figuring out how to make AI work for clinicians. So with that, let me start first by being a little provocative. I like to use this quote from Jeff Hinton, often considered the kind of the grandfather of deep learning. You probably saw him in this news this week that he resigned from Google and voiced concerns about where AI in general is headed. He said this in 2016, so 7 years ago, said, "I think if you work as a radiologist, you are like Wile E. Coyote in the cartoon. You're already over the edge of the cliff, but you haven't yet looked down. There is no ground underneath. It's just completely obvious that in 5 years, deep learning is going to do better than radiologist." And then he hedges a little bit and says it might be 10 years. Why is that's provocative for obvious reasons. I would like to share kind of our viewpoint that it was spoken well by one of the radiologists we work with yesterday, who said, "I'm a radiologist, I treat patients, and machines don't treat patients. And machines are tools, and I will take whatever tool is going to make me better." So I'd like to start with kind of that framework that Deep Health is building tools that we think will advance the field. And hopefully at the end of these slides, you'll might even agree with me. What's Deep Health? Founded about 8 years ago. Dr. Sorensen is a neuro-trained radiologist, worked in academia and industry for a long time, along with a computer scientist from Harvard. Myself came from MIT. We were acquired by RadNet, and I'll share more about them, almost 3 years ago. I'll share that we're very focused on the science. So you'll see some details on one of the studies we published in Nature Medicine. We have 3 FDA clearances. One is a triage tool, one's a diagnostic and detection tool, and one is a density assessment tool. And I'll get into what those all mean later. So I mentioned we're owned by RadNet. RadNet, if I go from the top left of these boxes, operates about 370 imaging centers across the United States, mostly focused on the coasts. A lot in California, a lot in New York, Maryland, New Jersey, Delaware. They have a lot of radiologists, many joint ventures. They process about 5% of the country's mammograms. High volume of CT as well, as you see on the bottom left. And then moving across the bottom row, they've acquired 3 AI companies. Deep Health is focused on breast cancer detection. Quantib is focused on prostate, and Aidence on lung. 2 other things to share about RadNet is you see their industry-leading IT solutions. So RadNet made the decision many years ago to acquire their own PACS and RIS systems so that they could customize and maintain a strong voice in what happens with their IT systems, as opposed to relying on vendors. That's played out very well for them and for the integration with AI. Last thing on the bottom right, you see equitable care. One thing that we're proud of, particularly I'll share an anecdote in breast, is that they are upgraded all their breast screening tools, meaning their mammography machines are all the latest Hologic HD, digital breast tomosynthesis. and you get the same mammogram if you come on the west side of Manhattan, or you go in the Harlem. You get the same machine. That's something that RadNet's very proud of, and providing the best care across clinics. That's a little intro to Deep Health and RadNet. Let me share kind of the meat of what I want to talk about to give you the AI industry perspective. So first, I'll give a little refresher on breast cancer. That's good background for the rest of the talk. Talk about how we built a state-of-the-art AI model. It's not easy. And then go from there to how do you build a commercial product. So having the model doesn't necessarily mean you have something to sell to anyone. And then 4, along with that, is you need regulatory clearance if you're going to market this device. And lastly, something that I think many take for granted, that, well, if you have regulatory clearance, then people line up to buy your product, right? And there's a lot more to it that drives adoption. And one of the key things that we focus on is clinical evidence. At the end of the day, this has to provide value to patients, to users, and that the FDA clearance does not imply that you've provided enough clinical evidence to convince users to use it. So with that, start with the breast cancer refresher. So you probably are aware 1 in 8 women develop breast cancer in their life. It's about 250,000 are diagnosed each year, and about 40,000 die each year. Turns out it's very correlated with age and race. So these charts and graphs are from the American Cancer Society. What they show is that generally, as you get older, your chance of getting breast cancer goes up. And that's why we have screening programs starting generally at age 40. You may have seen the news this week that the United States Preventive Services Task Force updated their guidelines, or they've put out a draft version of updated guidelines, which says that they now recommend, instead of starting screening at 50, starting screening at age 40. And that brings their recommendations more into alignment with the medical societies. For example, American Cancer Society has, the American College of Radiology has recommended this for a long time, that screening start at age 40. Other societies have similar recommendations, and hopefully that'll make an impact on patients. So if you look on this chart on the right, your probability of being diagnosed with breast cancer goes up quite a bit around the age of 40. And if it's diagnosed there, it can have a big impact on patients who might otherwise have it undetected and show up at a later stage in their 40s. That can have a big impact on the life. So mammography is generally recommended here. I say every 1 to 2 years, starting at age 40 to 50. Hopefully now we've kind of established 40. About 2/3 of women in the United States are compliant with that. So in general, there's just an issue of getting women to, all eligible women to show up for screening. And since screening has become widespread, the diagnosis has gone up, but mortality has gone down. So you see on the left, figure 6, from pulling these again from the American Cancer Society, showing that diagnoses have gone up, but the number of deaths has gone down. There's still a challenge in that reading screening mammograms in particular is challenging. You're looking for a needle in a haystack. So the several groups try to monitor this. It's difficult to get exactly what performance is across the country, but there are a few groups like the Breast Cancer Surveillance Consortium or the National Mammography Database who track statistics of readers and see how many are in the recommended ranges. And what is was surprising to me when I got in this field is there's a lot of radiologists performing outside what's considered an acceptable range. You see there highlighted in red recall rates, the percent of radiologists that are in the low performance range, it's about half that have a recall rate that's generally too high. And down at the bottom, you see cancer detection rate of less than 2.5. There's about 28%. Many would argue that 2.5 is much too low of a threshold for what's considered acceptable, that you really, if you want your loved one getting a mammogram, you would want them to go to someone who has a much higher cancer detection rate. So while overall screening for breast cancer works, it's really hard, and many cancers, unfortunately, are missed, and many patients are recalled without having cancer. I move. So to put a few numbers in your head, these are very ballpark. If 1,000 women get screened, about 100 are recalled. So that's about 10%. What I showed you on the previous slide was 5 to 12% is recommended, and many are above this 12%. But just as a very ballpark number, let's say 100. Out of those who come for diagnostic workup, about 15 will get biopsied, and about 5 will get diagnosed with cancer. Now, you notice that 5 number per 1,000 is twice what is considered acceptable. Now, why did we decide to focus on breast cancer detection? Well, as I described in the previous slides, this is hard, and there is a need for improvement. A lot of women die from breast cancer, and many go undetected on screens, and there are many women who are recalled without having cancer. We could make a difference there. It would that would be a direct benefit to patients. On the second line I have there's a financial opportunity. So there's more than 39 million mammograms performed in the United States, and they're reimbursed fairly well. So we can, this is an area where you can actually build a company. And that's what we're working on. We have to build something that's sustainable. The last row there is technically feasible. What this means is, in mammography in particular, there are strict guidelines put forth in the Mammography Quality Standards Act, or MQSA, that says how images are to be acquired. And so the data is actually quite standardized, and then we can train on that. We also have the outcomes, because you have to track diagnoses. So we know which patients got cancer based on the biopsies. And that gives you a more solid ground truth. So on one hand, we have more standard images, and on the other hand, we have good ground truth or labels to train the algorithm on. So this makes it a much more tractable problem than if if your outcome data is subjective, it makes it harder to train something that's consistent. So it was the intersection of these three things that you have a medical need, there's an opportunity to build a sustainable company, and that this really is a pretty good match, a great match for AI in medical imaging. So that's why we landed on breast cancer screening. So the next section is, I titled this Building State-of-the-Art AI. So I'm going to reference a paper that we published a couple years ago in Nature Medicine that describes the algorithm we built. And here it is. I'll walk you through this. So this is a model using deep learning that's trained to combine both weakly and strongly supervised training, and I'll explain what that is, on both 2D, which is full field digital mammography, and 3D, or digital breast tomosynthesis. So if we walk through this figure, you see there in stage 1, we had training data at a patch level, meaning we had individual regions of interest that we knew turned out to be cancer, and others that we knew did not. And we trained those individual patches so that the model could distinguish between this ROI is cancer and this ROI is not cancer. Now, that's not what happens in practice. We wanted something that could run on the whole image and find where those patches are. So we also trained on the whole images so it could detect where these patches are. And you're seeing that in stage 2. In stage 3A, you see that we also were able to design our architecture in a way that it could also be trained on image level labels. So it can be challenging to get high volumes of this very localized data. And so we had a lot that was annotated, and we also had some that wasn't annotated, and showed that we could still get better performance by training on both. The other interesting thing about this is if you follow the green arrow down to stage 3B, in that one, we were able to train a model that would work also on DBT or 3D mammograms. Sometimes is referred to as transfer learning, where we took what we'd learned on these 2D images, and we're able to apply that learning now to DBT mammograms, which are quite different, where you get a stack of slices as opposed to just one image per view. And on the left of this little box, it says creation of MSP images or maximum suspicion projection. On the next slide, I'll show you what this means. You see on the top where it says DBT planes, you have a bunch of planes there, and some of them are darker. And then you see on each one of those, there's a different color little box. And those boxes are then projected down onto where it says synthetic 2D. So maximum suspicion projection means we're finding the XY coordinates that are most suspicious, the most suspicious spot in that XY coordinate, and then projecting it down onto a 2D image. And then we take that, I'm going to go back to my previous slide. We take that image and train on that, which allows us to get performance to generate localization and scores on our 3D model. So what goes in on the left are 2D images or a 3D stack of images or DBT stack of slices. And on the right, we end up training a model which can output for us localization and scores indicating how suspicious something is to be cancer. That's kind of a long description of part A here of what went into building the data collection and the architecture of building these models. In part B, you see here on the right what the training data sets were. We collected from several different sites. We needed a lot of cancer data and a lot of non-cancer data. It's generally important to get more cancers. These are rare, and that the model needs to see more examples of what's cancer than what's seen in the general population. So if you go back to that table I made, 5 in 1,000 women end up being diagnosed with cancer. You need a lot more than 5 in 1,000 for your training set. At some point, you don't get a lot more value from training on more normals, but showing it more examples of cancer helps. This was a lot of effort. This whole training process going into things like acquiring the data, annotating, cleaning the data, developing pre-processing steps for the images, developing this architecture, experimenting with many different architectures, fine-tuning the models, post-processing. This took years of work. If I then go to, I'll just show you two examples of this kind of clever twist of using a maximum suspicion projection. You see here on the left is what the default synthetic looks like. And the default synthetic means for any given DBT stack of images, what's also provided to the radiologist is a synthetic view of those. So before DBT, you had one image per view. And when there was a switch to DBT, they kept that one image per view, but instead of using the FFDM and the DBT, which requires 2 exposures to the woman, what you can do is only do the DBT and then create a synthetic 2D image. And that's very useful for reference. So if you're scrolling up and down through the slices, you can also look and see the one view of everything. So that's what's being shown on the left. What's being shown on the right is this maximum suspicion projection. Sometimes we call it a D view you see there on the image. And you can see on the right image, that mass in the back looks more conspicuous than on the left. I'll show one more example of this, where something you can see it shows up much better on the right than it does on the left. And then we're able to feed this into the final stage of our model for classifying whether or not there's cancer there. And you can see on the left, the malignancy score is a lot lower than the malignancy score on the right. Now, I'll transition a little bit to something else in this paper, and that's really that the goal of screening mammography is to detect cancers earlier, and we'd like to detect that as early as possible. And so in testing this algorithm, one of the first things that we did was compare our performance to some radiologists as a benchmark. Now, one way you can do that is you go get the index exam, meaning the exam that was used, where the cancer was detected, the screening exam where the cancer was detected that led to the biopsy for the diagnosis. So if you're going back to collect some data and say, where do I find some examples of exams that I know have cancer that I want to test how well the AI finds those, you can go find index exams where you go look at where the biopsy happened, and then you see, was there a screening exam relatively soon before that? And we used a time window of 3 months to go find those exams. But then we also found what we called pre-index exams. So that means we went and looked 9 to 24 months before the cancer diagnosis, meaning the biopsy. And those ones, we were specifically looking for things that had been a BI-RADS 1 or 2. Now, just very briefly, BI-RADS 1 or 2 means you're not recalling it. BI-RADS 0 on a screening exam means you're bringing back the patient for further workup. So BI-RADS 1 or 2 means that the radiologist didn't see anything that was worth working up, and yet they were diagnosed with cancer 9 to 24 months later. So we went and found a bunch of these exams to also test how well the AI would find such, earlier cancers, or 9 to 24 months before the biopsy, as opposed to only 3 months before the biopsy. We also had to collect negative exams, and the way we do that to make sure that they are negative is you find a screening exam that's a BI-RADS 1 or 2, and then make sure that 24 months later, they have at least one more BI-RADS 1 or 2 exam. So then we can confirm longitudinally that this person is still not being recalled in the future. Therefore, we're more confident that indeed they don't have cancer now. So we collected this data set and had the AI run standalone, and then without the readers having access to the AI, they read these cases. And in this study, we had 5 fellowship-trained full-time breast imagers read these cases. And what you're seeing are the results showing, you see there in A, there's a red curve. That's what the model, that's the ROC curve from the model. The readers are these individual dots, and they were indicating whether to recall or not, which means they don't have a curve, they have one individual point. Did they recall or not? And then they get a sensitivity and specificity point for each one of them. So our curve is generating, our model is outputting scores so that we can generate a curve. And you'll notice that the curve is above all the radiologists. What that means is that any point where they're operating, the sensitivity of the model is actually higher. And you see that in B. For example, if you look at reader number 1, reader number 1 was very specific. They did not recall very much, but they only caught half the cancers. Their sensitivity was about 50%. And the model was about 20% higher than them. We did the same thing with these pre-index cases. So we took for the same patients, we took all the ones that had a screening exam the year before, And we did the same experiment, had the radiologists read those and ran our model on them. And you should notice two things. One is that everyone's performance gets lower, meaning the sensitivity is going down. And that makes sense because these are things that were not recalled in practice. So for each of these exams, there's something that's in the image, but maybe they didn't see it, or they saw it and didn't think it was actionable. That's the interpreting radiologist, meaning clinically, that's what happened. But when we had 5 readers reread these, they also had a hard time finding them, and the AI performed worse. But the key here is that it still was above the radiologist's performance. Now, there are a lot of nuances to this study, but in this particular study, these were very encouraging results that we could say we have a model. Not only do we have, we can get some AUC value that seems good to us, we can benchmark it against somebody, and 5 fellowship-trained breast imagers seems like a decent benchmark. I can show you a couple examples of what this looks like. So here you have the index images, the images from the index exam. There is a cancer there, highlighting it. There was a pre-index exam from 13 years before. You can see it's not as conspicuous, but that's an example of we'd like to catch it on where it is on the left side as opposed to the right side. Okay, and with that, I'll transition to how do you take this model, and at that point it was a model, and turn it into a commercial product. That means it has to be useful to somebody. And that's where we've developed a product called SageDX. So I mentioned at the beginning that we have 3 FDA clearances. One is for a triage product. In a triage product, you can flag something as suspicious, but you can't localize anything or say give any grade of how suspicious it is. SageDX is called a computer-aided detection and diagnosis device, or CADEX. And that means that you can localize and you can provide an assessment of how suspicious it is. So we provide 4 suspicion levels. We chose this to keep things simple, meaning you could provide numbers to a user or colors to a user, but we said here are 4 categories, and we think these categories are actionable for you. There's a finding suspicion level, meaning for each box that we identify in an image, we assign a suspicion level to it, but also for the whole case. And this is what it looks like. This is all the demo you get, because the demo isn't very exciting because it's meant to be simple and fit into the radiologist's workflow. So this uses the same mechanism to display CAD. So on a mammography workstation, there's generally a button where you can toggle on and off CAD markings. And our device uses that same structured report to store the information so that the user can then just toggle on their workstation while they're reading and see what the AI thinks. That means that we're running the AI as we're getting the images as they're acquired. We're running the AI, and then we're storing the results in the packs. So when the radiologist goes to read, when they retrieve the cases, the images, they're also receiving the AI results. So you see there on the right breast, there are 2 high boxes, and meaning the patient's right. And on the left, you see 1 low box. And that would indicate this is the most suspicious thing in the image, but low means that we don't think it's suspicious. But the right, when we say high, that means that these are suspicious. The user could view this on their work list, but the main value is while they're reading. Now, probably have the question, what do these categories mean? And we created this little diagram to explain what they mean. So here I have an oval of about 5,000 dots. And if you imagine each of these dots as one patient getting a screening mammogram, then you'll have about 25 cancers, which I'm representing here with X's. And then if we run our AI, you're going to get these, each exam will be assigned a suspicion level. And for illustrative purposes, I'm coloring them like I colored them before. The high is the red, intermediate orange, and yellow is low, and green is minimal. Now it kind of looks like a mess here, but if I sort them, hopefully you can see the value. So the highest, the red is a small fraction of the cases. It's actually 5% of the cases. So you see this table on the right. The high is 5% of the cases, but it's 87% of the cancers. So the cancers are being concentrated in these most suspicious category. Then you have the intermediate, which is the next 20%. You have about 10% of the cancers. And then low, there are very few, and minimal, there's close to none. This data is coming from our FDA study, and out of 136 cancers, there weren't any that showed up in the minimal category. Eventually, if you look at enough, you'll find one that's in there. So that's the device that we developed and got FDA cleared. The idea is that by showing this to the radiologist, we're providing an aid while they're reading the screening mammogram. I think it's useful to spend a little time talking about regulatory clearance because I'm here to give the industry perspective, and this is a requirement. If you are going to market a device to end users, you need to show evidence to the FDA that it's going to do what it says and that it's safe and effective. And there's really a lot more that goes into this than I was aware before getting into this industry. And I think that might be useful for you to know as well. So one thing is you have to have a quality management system, meaning you have things like design controls, and I'll share a little bit that in a second. You are assessing risk and showing that it's safe. You've evaluated things like what are the potential cybersecurity risks that a device could have and make sure that you're mitigating those. You also have to show that you validated the tool in some way and that you have data that you can show to the FDA. That gets you through to clearance, but then you would continuously, post-clearance, you need to still monitor what your system is doing and continuously updating, ensuring that your device is working as it should. And I'll go into each of these in a little bit more detail. Here I pulled this from the FDA website. There are many documents that outline what you have to do. I like this one because it said there are a number of steps you have to go through, from setting requirements for what your device has to do. You have to come up with a design that meets those requirements. You have to come up with tests that show that you have implemented each one of those design items correctly and that there's some acceptance criteria and they have to pass all your acceptance criteria. And then you have to show that it's actually doing the thing that you wanted it to, meaning providing the benefit that it should that it should provide. And you have to test that and demonstrate it with data, and then go through. And not only that, do that whole process, but you have to go through and assess what might be risks at any step of the way. I mentioned cybersecurity is one. Could someone hack into your device and do something malicious? But there could be other risks, like what if someone unplugs your device? Is it going to crash? Can it restart? Is it going to delete data? So on and so forth. And then you have to show that you have to mitigate those risks. And once you have a device, you continuously have to monitor, improve that design. If you find, I didn't know that someone could unplug it and it would crash and cause problems, how are we going to update it to make sure it won't have that problem again? Now, this is all built around, say, you have a model, but there's a lot more that goes into building the product. And that's what I wanted to convey. I mentioned that there's validation testing. So I'd like to spend a second on this. you, for a CAD-EX device, so showing that you can aid the radiologists in their detection and diagnosis, what the FDA asks for is a reader study. What this means is that you go gather, retrospectively gather exams that you know are cancer or are not cancer, and then you have the radiologists, a group of radiologists, read those without your device and then with your device. And you put a washout period in between so that they generally forget this. So what you can do is say, start reading these cases, and then a month later, we're going to have you read with the software, and we'll see if your performance changes. Or you can do it vice versa. Some of the readers will start with the software, and then later they'll read without the software. And what I'm showing you here are the ROC curves of the readers. So this is not the performance of our device, it's the performance of the readers. The blue line shows the curve, their curve without the device, and the red line is the curve with the device. And improvement means you're going up and to the left. That's perfect. That would be perfect if you could, if the curve went straight up and to the right, showing that you're very sensitive and very specific. And so as it goes from blue to red, we're showing an improvement in performance. And this was statistically significant and demonstrated the FDA that the device is doing what it says it can. Now, to dig in a little bit more to that, we selected half our readers in this case. So there are 18 total readers, half to be generalists and half to be specialists, meaning they're focused on reading breast imaging. And what you can observe is that the performance, so these are the individual AUC or area under the ROC curve for each of these radiologists. You'll see on that in general, the generalists do not perform as well as the specialists. And that might make sense on this task. This is what the specialists spend all day doing. They're probably better trained for it. Therefore, they have better performance. What was maybe even a little surprising was how much better the generalists got. And you see there on the left, they're now all approximately in a similar level, and have gotten much closer to the performance of the radiologists, of the specialist radiologists. So a couple of observations. One is everyone got better. In some reader studies, they'll show that, well, most got better, but a few didn't get any better, or some got worse. You'll also see in the middle here, we have the mean performance. And what you see is that if you look at that red square, that represents the performance of the mean performance of the generalists with our device. And that's actually higher than the mean performance of the specialists without the device. And that's very encouraging because it suggests that the AI could help generalists get closer to the level of specialists. And most mammograms in the country are actually read by generalists. There are just a lot of mammograms to be read, and there aren't enough breast specialists to read them all. So most mammograms are read by generalists, and that's where the most improvement could come from. Okay. One topic I noticed it was on the agenda today, I believe, is bias in AI. Now, this can affect humans. It can also affect AI, right? This was an article from a few years ago, and that's it's important to consider. So as in this study that I showed you, we made sure that we collected data from a diverse population. So you're seeing their race, ethnicity in the table on the left, and how many from each group there were. Some of the groups that's hard to collect a lot of data on. And then on the right, you're seeing the performance with and without the device over those subgroups. And what we're seeing is across all race and ethnicities, there is a substantial improvement. So that's important to test. Other subgroups, I'll show you two more. One is across density. So this has also been in the news recently with the FDA requiring reporting of density to patients across the country. There were many, it was already required in most states, but now it's a federal requirement. So we want to show what's our radiologists getting better on dense breasts as well as non-dense. And you can see on that left plot, if you look at the blue, radiologists were actually a little bit better on our cases on dense, which was a little surprising. What was very encouraging is in either case, whether it was non-dense or dense, they improved on each one. And then I'm showing you on the right, if you group the cancers by lesion type, so it's either some soft tissue density, or it's a calcification, or in some cases it's both, does it help on both? We found it helps more on, a little bit more on calcifications, but that we had, it was statistically better on either one, either soft tissue densities or calcifications. The last slide in this section I want to share with you was, once you've deployed an FDA cleared product, it doesn't just end with clearance or putting it in the field. You want to monitor it. So one of the things that we've been doing is checking these suspicion levels and seeing if they behave the same over time. And this graph is showing you that, over 6 months last year, as we were tracking this, the exams in these categories was staying constant. And that's what we want to see. And we want to be aware if there would be some change. Okay, so now to the last part, I think, is what do you need to adopt? Just having FDA clearance often is not enough clinical evidence for users to feel confident. There are also different ways that people might use such a device. So I'm going to share a couple of these, and I'll try to keep it within time, so I may skip over a few slides. But just to, this is kind of a fun example. If you have not seen this paper that was published in PLOS One, my question here is the AI practical, or is this really just a proof of concept? What they did was they trained pigeons to classify cancer on pathology slides, and they demonstrate an AUC of 0.99, which would appear to be very good, right? Now, I put this in to be a little provocative and to think, what performance do I need to see to, trust the AI, so to speak? I don't think most people would trust pigeons, but we need to provide clinical evidence that the AI works. And there are tons of vendors out there, and our observation is it's very hard for the clinicians to distinguish quality. So I bring up these questions of how much evidence is enough. For example, is standalone performance good enough? If we tell you our device has an AUC of 0.93, is that enough? Or is it 0.97? Is that enough? I've showed you a comparison to readers. Is that enough? Is the reader study performance? Did that convince you? Is it the FDA clearance? And you think, well, is that enough? Or do you need more clinical results? And if you're going to look at clinical results, what do you need? Do you need, how many mammograms would you want to see it on? How many users? To what degree do you see a change? So this is also in the paper. I'm just showing the AUC values on several different data sets. These were the curves I showed you before, showing the standalone performance of our model compared to the readers. I showed you the reader performance from our study. But what we have found is generally that's not enough for people to say, yes, I trust, love it, I've seen enough, don't need to see any more evidence. So let me share with you two quick pieces of evidence. And I'm going to speed up a little bit here. We did a study with our device where before we showed the outputs to users, so we're generating scores and suspicion levels, as I described before. Before we actually turned that on and had the radiologist use it, we ran it in the background, and then we compared that to what the radiologist did. And we collected data for 1 year. We collected data at 148 clinics with about 500,000 mammograms. It was unenriched data. We ran on everything. And then we collected out all the data that came from that, as well as the radiologist, did they recall the patient or not, as well as the biopsies. And then we continued collecting the biopsies information for another year. And what we found was, if you look at the cancer detection rate in those different categories, so this is the cancer detection rate of the radiologist in those different categories, you can see that it's much higher in the high category. It's about 15 times higher than the intermediate category, which has the performance that you would expect in the general population. So as I shared at the start, about 5 in 1,000 cancers in the general population are detected. And it turns out about 5 in 1,000 intermediate cases had a cancer detected. So if you use intermediate as kind of the general probability, the general surrogate for the general population, this high category of mammograms has way more cancers, and the minimal has way fewer cancers. And if I'm going to jump a couple slides and show you the recall rate. You can see that even though the cancer's detection rate goes up exponentially as you go from these minimal to high cancers, the recall rate of the doctors did not go up exponentially. It kind of went up linearly. And what that means is that the positive predictive value, what I'm showing you now on the right, is quite high in the high category, and it's very low in the lower categories. So to give you, to benchmark what this means, and just to review maybe quickly, so cancer detection rate is how many cancers per thousand screens you found. Recall rate is the percent of all patients coming for a screen that were recalled for diagnostics. Positive predictive value is the number of the percent of recalls that have a cancer. So if you recalled 100 patients and you found 5 cancers, that's a positive predictive value of 5%. And if you compare this to statistics that are published, like one example is the Breast Cancer Surveillance Consortium, you can see that high is like off the charts high. Intermediate, 2.8 on our graph on the right, is very close to the low end of what's considered acceptable, which is a range of 3 to 8 in the graph on the left. And then if you look at our low category, where it's 0.67, well, that's lower than the lowest PPV value of any radiologist. And then if you look at minimal, it's 0.28, which is about 10 times below what's considered acceptable. Now, if you're not used to looking at PPV values, it can be helpful to flip it in your mind, which is the recalls per cancer detected. So if you think PPV of 5 is 5 cancers per 100 recalls, that means you have to recall about 20 patients to find 1 cancer. Here we see that even though acceptable, the low end of acceptable is about 33 recalls per cancer, we're seeing in the minimal and low categories somewhere between 150 and 350 recalls to find a cancer in those categories. And what this suggests to us is radiologists could be much more selective about recalling low and minimal suspicion cases. So this could help with recall rate, but it could also help with, in the highs and intermediates, detecting more cancers. I'll show you one more piece of data. So in addition to looking at cancers detected, we also looked at cancers that were not detected. So for example, an interval cancer is one where you have, before the patient comes back for their next screen, they show up, perhaps they have a lump, they get a diagnostic image, they find cancer. So they had been screened, but before their next screen, cancer is diagnosed. That's an interval cancer. Or what we call an undetected prior here, and that means they did come back on their next screen. They still didn't have any symptoms, but cancer was detected at the next time point. So we went in this data set that we had, we went back and looked, do we have the AI categories for all of these exams where cancer was undetected? And we compared that to what we would expect the distribution of, we compared the distribution of cancers, these undetected cancers, to the overall distribution of exams. So I shared with you before when I was showing that big oval plot that about 25% of exams are in the minimal case, minimal suspicion level, 50% in the low category, 20% in the intermediate category, and 5% in the high category. And what we're looking for here is if the AI doesn't see anything, we would randomly expect there to be about 5% of the cancers in high. What we find is it's more than 4 times higher. So for the interval cancers, most of these cancers end up either in intermediate or high, which is encouraging, because that means a radiologist could use that information while they're reading to hopefully catch it at that stage, as opposed to when they come back with a lump. We found a similar pattern for these priors of undetected cancers. So this was one example where we were able to show a comparison directly to radiologists on 500,000 mammograms. I'll just summarize that we've done other testing where we've given the device to radiologists and their CDR goes up. We've also tested it where we used the AI to inform an additional review. So if we have the radiologist, if the first radiologist does not recall it and the AI said this was high, in some places they will have an additional review of that case by particularly an expert radiologist. And we found the practices implementing this have found many more cancers because of this. We had a talk at the Society for Breast Imaging showing that one practice, they found 50% more cancers. And if I just jump to that slide, or one before it, what's interesting here is you see CDR of these 6 radiologists. And in the blue, I'm showing you what they did on their own. And then in the red, I'm showing you how they were helped by having an additional review that was driven by the AI. And you can see that their radiologist number 6 was performing at a level much lower than the rest, and they get pulled up almost to the level of the others. And so what they observed at their practice is using the AI in this way, their performance, everyone got pulled up to some degree, and particularly those who were underperforming got pulled up a lot. With that, I think I'm almost out of time. I just want to give a quick refresher, just recap that we talked about building AI. There's a lot that goes into particularly a challenging problem like detecting a subtle cancer in screening where you have cancers are very rare. We talked about how you can turn what it takes to turn that model into something that's useful for a clinical user. And then everything that goes around packaging that so it can be FDA cleared and generating the clinical evidence so that the FDA will allow you to market it. But then going a step beyond is testing it in the real world, seeing how it performs compared to radiologists, seeing how it performs when radiologists are using it, testing other ways that you can get the most value of combining it with the radiologist to really provide the best care for patients. And with that, I'll try to stop a couple minutes early.